Graves' disease is an autoimmune disorder and hyperthyroidism is the most common feature. Graves' disease is caused by antibodies against the thyroid-stimulating hormone receptor which bind the receptor and lead to the continuous synthesis and release of T3 and T4.
In Graves' disease, autoantibodies are produced which act in the same way as thyroid-stimulating hormones, TSH, that stimulates the thyroid gland to increase its secretion.
It begins when thyroid-specific antigens activate CD4-positive T helper cells, which in turn stimulate the B lymphocytes to produce antibodies against the thyroid-stimulating hormone receptor.
The three types of autoantibodies that binds to TSH receptor currently recognized are: first, thyroid-stimulating immunoglobulins. These antibodies, mainly IgG, act as long-acting thyroid stimulants, thus activating the cells in a longer and slower way than TSH, thus leading to an elevated production of thyroid hormones. Second, thyroid growth immunoglobulins. These antibodies directly bind to TSH receptors and have been implicated in the growth of thyroid follicles. Third, thyrotropin binding inhibiting immunoglobulins. These antibodies inhibit the normal union of TSH with its receptor. Some actually act as if TSH itself is binding to its receptor, thus inducing thyroid gland function. Other types may not stimulate the thyroid gland, but they prevent TSI and TSH from binding to and stimulating the receptor.
There are few mechanisms in breakdown of self-tolerance in Graves' disease, which are central tolerance by clonal deletion and peripheral tolerance by deletion and inactivation energy. Central tolerance refers to mechanisms of tolerance acting during lymphocyte development in the thymus or bone marrow. Experimental studies show that central tolerance is mostly due to the elimination or inactivation of those T and B cells that recognize self-antigens. These cells are destroyed or inactivated after they have expressed receptors for self-antigens and before they develop into fully immunocompetent lymphocytes. Deletion of self-reactive cells at an early stage in their development has been termed clonal abortion or clonal deletion. In early fetal life, self-reactive lymphocytes that are part of the developing immune system are deleted when exposed to self-antigens. As mentioned above, new immunologically competent cells are generated throughout life, and this must be continuously deleted or inactivated also. Peripheral tolerance refers to mechanism acting on major lymphocytes after they have left the primary lymphoid organs. Not all genes are expressed in the thymus, so developing T cells cannot be exposed to all self-antigens. Therefore, additional mechanisms for tolerizing self-reactive mature T cells are necessary. Mechanisms of peripheral B cell self-tolerance are also necessary because after stimulation with antigen, B cell expands and undergoes somatic mutation, generating a population of B cells with new antigen specificities. Some of these cells may be specific for self-antigens. It is now known that at least two receptor ligand families play an important role in regulating T cell expansion in the periphery after contact with antigen, and these same molecules are probably involved in deleting self-reactive lymphocytes in the periphery. Peripheral deletion of CD4 T cells seems to be dependent on signaling through Fas. Mice, and when deficient in this pathway, fail to delete T cells and develop aggressive autoimmune disease. Sometimes T cells are not deleted but become specifically unresponsive to antigen stimulation. This is called clonal energy. If antigen is removed, these energetic cells recover their responsiveness with time. One of the molecular mechanisms responsible for inducing energy is signaling via CTLA4, a molecule expressed by activated T cells. Mice deficient in this gene get a severe autoimmune disease, and there is some evidence that human autoimmune thyroid disease is linked to deficient expression. Ways of autoantibodies involved in the disease are thyroid-stimulating immunoglobulin (TSI), thyroid peroxidase antibodies (TPO), and TSH receptor antibodies.
Now, we will discuss about the genes that related to the Graves' disease. There are several types of genes have been identified that are linked to Graves' disease. The first one is the genes that weaken or modify the response of the immune system, which is the CD40 genes, CD25, CTL4, FOXP3, and HLA genes, particularly HLA-DR3. And the second one is the genes that directly link to thyroid function, such as the thyroglobulin and the thyroid-stimulating hormone receptor genes. The thyroglobulin gene produces a thyroglobulin, which is a protein that is found only in a thyroid tissue and plays a role in the production of thyroid hormone, while the TSHR genes, or the thyroid-stimulating hormone receptor gene, produce a protein that is a receptor and bind to thyroid-stimulating hormone. The exact underlying manner that genetic and environmental factors interact to cause a Graves' disease is not fully understood. Additional genetic factors, known as modifier genes, may also play a role in the development or expressions of Graves' disease.
Diagnosing hyperthyroidism is done by measuring blood levels of TSH, T3, and T4. If it's due to primary cause, TSH will be low and unbound thyroid hormones will be high. Once hyperthyroidism is confirmed, a radioactive iodine uptake test and thyroid scan hope to determine the specific cause of the disorder. If blood level of TSH are normal or high, this point to pituitary tumor, which can be confirmed by injection of thyrotropin-releasing hormone.